So today we have to finish with types of convergence. Different types of convergence of random variables. Okay, so different types of convergence of random variables, right? So we know that there are four, but we just are going to look at 3 of them. So number 1, 2, and 3. So the first one is convergence improbability. So we say that Xi n convergence improbability to Xi if, let me write like that, yes, if for every epsilon greater than 0, the probability that the difference between Xi n minus Xi is greater than epsilon tends to 0 as n tends to infinity. Right? So this is what we call convergence improbability. And then we have convergence, well, the first one wasn't convergence. This is the second one that we studied actually. We call it second. This the first is almost surely. So we say that Xi n converges almost surely to Xi if the probability of such omega where Xi n tends to Xi is 1. Right? So almost surely means that all the elementary outcomes in which there is convergence, the measure of this omega is 1. Right? So this is almost surely. Again, please. You said something? No? Okay. And then we have finally convergence in distribution, or weak convergence, right? And this happens if for any function f such that f is bounded for any function f such that f is bounded and I don't remember the other. So we need bounded and, well, we have other condition for f, but I don't remember, and something. You can check that. We already did this. Then the expected value of f of Xi n tends to the expected value of f of Xi. Right? And this is by now not very clear because why, I mean, what is the meaning of this, right? So why do we need this? This is not very clear by now, but we will get it. Okay. So this is these are all the types of convergence that convergences that we have, and we know that this one, for example, means. So this one means. So the third one means that. So we have that Xi of n tends in distribution to Xi if and only if the Ctf of Xi of n in x tends to the Ctf of Xi in x for every x. Okay, where x are the x such that, okay, let me write like that. For every x such that x such that f of, okay, like this, such that f of Psi is continuous in X. Okay, and this is that we call a theorem, Alexandrov theorem. So that's it. This is all that we know by now, right? And this is important because actually when we are proving the weak law of large numbers, and there's something that we call also the strong law of large numbers, and when we prove today or maybe next class the central limit theorem, then we will be talking actually about this. So for the weak law of large numbers, we can state it as follows: if Psi1 plus Psi2 plus Psi(n), right? So these are independent, identically distributed random variables, right? And we call, let's say that all of this is just Sn. Then the weak law of large numbers tell us that Sn over n tends in the probability to A, where A is just the expected value of Psi1, for example, right? So the weak law of large numbers is just this. Somehow is this. Okay, so here, this. This is the weak law of large numbers. So the average value of this sum tends to the expected value of Psi, but not only tends to the expected value of Psi, but tends in probability, right? So this part is important. It tends in probability. So, we already said that this is called weak law of large numbers because we can change this P by W right here because of weak. So we also call this, so we can write here W. So weak converges. So that's why this is called the weak law of large numbers, right? In the same way, if there's a weak law of large numbers, then there's a strong law of large numbers. So let me write over here. Yeah. So the strong law of large numbers, right? The strong law of large numbers. In the strong law of large numbers, we have almost the same, right? But I'm not going to state exactly the theorem, but the difference, so we need to write this as n over n tends to A. The only difference is that instead of writing P, we have to write almost surely here. So this is, in general, this is the law of large numbers. So there are two different, and actually there are more, but there are two different main, the board is not visible. I see. Sorry. Yeah, not a very good. You sure? Just don't break it.
If something happens, you say that the woman or what she did.
All right, thank you. Okay, let me repeat this again. So look, weak law of large numbers and a strong law of large numbers. What's the difference? The difference is that here we have a convergence improbability, or weak converges, right? This is why this is called weak law of large numbers. And here we don't have a convergence improbability. We have almost convergence almost surely, right? So we can see it here. So almost surely convergence. That's the only difference. How this random variable converges to this number, right? And how this random variable converges to this number. That's the only difference between the weak law of large numbers and the strong law of large numbers. This one we prove it. It's not hard. We prove it using the Chebyshev inequality, and for that we need the variance to be defined. But there are some cases in which we can prove it without using the Chebyshev inequality, and this is a different way. It's called the Him-Chim's form of the weak law of large numbers, but we are not going to prove it, right? So maybe we need variance or maybe not, right? We can prove it in both cases. This one is hard to prove. This is difficult to prove. So we are not going to prove this, right? Just is enough to know that there is such thing, right? So look, we can see that the types of convergences that there are important for us, right? Now, yeah. Now, what do we need next? Okay. So.
We can take a picture of the convergences.
Okay. So we have that. Great. Now, why this is strong and why this is weak? Well, because we have the following, how to say, so they are connected in the following way. If this is convergence in probability, then this is convergence in distribution, and here we'll have convergence almost surely. So from convergence almost surely follows convergence in probability, and from convergence in probability follows convergence in distribution. Okay? So if we know that some random variable converges in almost surely, then it means that it converges in probability and it converges in distribution. If we know that some random variable converges in probability, then it means that it also converges in distribution, right? And this is true always, but this is not true in general, and this is not true in general, and this is not true in general, right? Yeah, you can file your test if you want to look at it. Yeah, and don't forget to put it back. Okay. 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 Now, there are some examples why this is not true, right? Let me show you just one. Let me show you that if we have convergence in probability, then it doesn't mean that we have convergence almost surely. Let me show you an example. This is a famous example. So that from probability doesn't follow convergence almost surely. So imagine the following, that we have a sequence of the following random variables. So the first one, so here we have one, and here we have one. All right. So the first one, the first random variable is like this. Okay, so it's the indicator function from 0 to 1. Okay, this is psi 1.
So why is the probability derived? What is the expected value of the y?
This is the random variable, and this is omega. So this is a random variable, psi 1, random variable. Okay, now the next random variable So what I want to do, look, I want to find a sequence, right? I want to define a sequence such that it converges in probability, but it doesn't converges almost surely, right? A sequence. So I'm going to try to draw that sequence here. So this is the first one. So no, this is not the density. This is the function itself. Do you understand the difference? This is important. Between, okay, so look, there's a random variable psi. A random variable psi is a function, right? Like this one, this is a function. For this function, we can define the density, right? This is a different function. So this and this are different, okay?
But since the probability of psi is the same for all values of psi.
Okay, what are the possible values of psi in this case?
From 0 to 1.
No. Daniel, tell me, what are the possible values of Psi? Psi1. No. Why? Maybe I'm not. Wait.
Okay, you want us to minus infinity.
Nope.
Maybe 0 and 1,
0 and 1, yes.
0.5.
Maybe because of this. Only two values, 0 and 1. 0 and 1, right? Psi is a random variable which takes only two values, 0 and 1. This is something different. When we have this and it's like this, then it's true what you're saying. So Psi can take all these values. There's a huge difference, all right? So this is the random variable Psi. It looks like this, okay? Now, the next one is almost the same, but from 0 to 1 over 2 here. This is Psi2. Then the next one is from 1 over 2. Here we have 1 to 1. Then the next one is going to be half of this. So it's going to be from 0 to 1 over 4. Mm-hmm. So look, these are different random variables. These are a sequence of random variables. So every time we just, so we have this, then half, and from here to here. Then half of it, so 4, 1 over 4, then the next is going to be from 1 over 4 to half, then from half to 3 over 4, and then to 3 over 4 to 1. The next one is going to be from 0 to what? Yes, and so on, right? So that is the sequence that we have. Okay, so every time, this, 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 okay?
Up until it's closer to the 0 to 1 of the left one.
Yeah, so like this, then it goes like ta 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 ta, but and then half of it, and then again all of the ta 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 ta, and then half and so on up to infinity. This is the sequence that we have. Okay, I need to prove that this sequence converges in probability to 0, but it doesn't converge almost surely. Right? So it means that we will have some sequence like this, right? That converges in probability, but doesn't converge in almost surely. Okay. Why it doesn't converge almost surely? Because what does it mean convergence almost surely? Look, almost surely is here. Take all the possible omega, take all the omega in which we have convergence. And the measure or the probability of such omega is going to be 1. So again, take all possible omega in which we have convergence, because there are some omega in which we don't have convergence. But we need that the probability of such omega in which we have convergence is 1. Okay? So, look. Now, what is omega in this case? Omega is all the points between 0 and 1, right? Omega are all the possible values from 0 and 1. Now take any value that you want. For example, I don't know, this one, some x here. Take any value here. What value do we have for x in this case? I don't know, x being, well, here for example, yes. So what value do we have for x in this case? 1, right? So what is psi 1 of x is what? Is 1. Yes? Yeah? Now, this x is over here. Now, what is psi 2 of x? 0, right? And then we go back here, and then x is over here, right? So psi 3 of x is 1. Well, because it's here. Look. Yes. And we keep going, and we have 0, 1, 0, 1, 0, 1, 0, 1. So we have the following sequence. Do we have convergence here? So if we know that we have 0, 1, 0, 1, does this converge? No, we don't have any convergence. Right? You can see it? Yes, there's not convergence. Convergence is when this going like this to some point, right? Then we have convergence. Here we don't have convergence because we have like this up to infinity times. So there's not convergence, right? And this is true for x being any number from 0 to 1. So for any number from 0 to 1, there's not convergence. So what is the probability? So what is the measure of all the x, right? In that case, x was omega, in which there is convergence? It's going to be 0. So look, for every x here, there is not convergence. And these are all the possible values of omega. So the question is, the probability, so what is the measure, yes, the measure of omega such that psi n tends to psi? So in how many omega here, so in how many of these, there is convergence? So psi n tends to something. Nowhere. Okay, nowhere. So this is 0. I hope you get it. Okay, so look, again, so we don't have almost surely. There is not convergence almost surely. Now, what about convergence improbability? Convergence improbability means that the probability, so let me, in a different color, this one. The probability that psi n minus psi is greater than epsilon tends to 0. Let's say that psi is 0. Okay? So what is the so okay. Yeah, let me do it here. So we need probability that the absolute value of psi n minus psi is greater than epsilon tends to 0. If we have this, then it means that we have convergence in probability. Now, let's say that psi is 0. Okay? So, for this case, what is the difference between psi 1 and 0? Wait, just say this. Probability that this is greater than epsilon tends to 0. This is greater than psi n minus psi. Just a second. Psi 1 minus 0 is this one. This one. Just a second. How is this here? So the probability that psi n minus 0 is greater than epsilon is equal to 1 over 2n. So look, every time, so we have here 0, right? This is 0. Every time we are closer to 0 by half, because that's what we are doing, right? So we have this, then half, right? Then half of it, so 1/4, right? Then 1 over 8, and so on. So the probability that psi n is different from 0 is always is always 1 over 2 over n. So 1 over 2, 1 over 4, 1 over 8, and so on, right? And if n tends to infinity, then this tends to 0, right? Because this is closer and closer to 0. Okay, so this function, psi1, psi2, psi3, psi n, this is closer and closer and closer to 0. Then this is like this, so this tends to 0. So it means that psi n tends to 0 in probability. Okay, but psi n doesn't converge to anything, right? Well, to 0 in this case, almost surely. Okay, so this is the example that we have, and for every case from here we have different examples. I'm just using this one and no more, right? And there are many things. This can take forever to prove and to study like the meaning of all of this, right? But that's enough. All right. So that's it. So now let's move to something else. Look, we already know. So before here, we have we already used induction, convergence improbability. We already use it. We already are using convergence almost surely, but we haven't used convergence in distribution, right? And we have it, so we have convergence in distribution. So why do we have it, right? So why do we need this? Where is it? Right? Where do we use it? So, and this is going to be a question for sure in your exam. Like, tell me the types of convergence that we have, and tell me where do we apply it? Yeah, but you don't have to prove anything. You just have to tell me. We have convergence in probability. We apply it for the weak law of large numbers. We have convergence almost surely. We apply it for the strong law of large numbers. And we have convergence in distribution, and we apply it to the central limit theorem. And this is what we are going to do now, right? So the central limit theorem is something that I'm not going to talk about right now. I'm going to talk about something that we need to prove the central limit theorem. So our main goal right now is to prove the central limit theorem, right? To prove the central limit theorem. This is the main goal for today and tomorrow. But to do that, we need to introduce something called the characteristic function. Characteristic function. Okay, this is a very important topic here. So look, remember, we had the following thing. For every, okay, now. Yeah, so we have probability distribution pi, right? And p, sorry. And for every probability distribution, we define the probability distribution function, the Ctf, right? So for this, we define the Ctf. And what is the Ctf? Again, so The Ctf is just the probability of this, so from minus infinity to x. Okay. So this is the Ctf. So the CDF, we use it to describe the probability distribution. So we have a probability distribution, and we use the CDF to describe it. And the CDF is just the probability that psi is between minus infinity and x. Okay, so this is the CDF. And we have used the CDF to get the probability density function, and we use the CDF and the probability density function to find the expected value, the variance, the covariance, and the distribution of anything that we want. Right? So everything that we've been using by now is this, the CDF. This is everything that we've been using. And this is one method. This is the first method that we have. But there's a different method that we have. And this is using the characteristic functions. So if we have a probability distribution, okay, we have two different ways to describe this probability distribution. We can use the CDF, or we can use the characteristic function. Two ways. Sometimes it's better to use this one. Sometimes it's better to use the characteristic function. It depends on the problem that we have. So for example, proving the central limit theorem using the CDF is hard, it's difficult. But using the characteristic function is very easy. Okay? So again, what's the difference between the characteristic function and the CDF? The difference is that there are different tools to describe the probability distribution. Right? So you have two different tools, and you can absolutely describe everything using them independently. Okay? So what is the characteristic function? Is this function. So the characteristic function of random variable psi is just the expected value of e to the I psi x. So this is the characteristic function of a random variable psi in the point x, right? Characteristic function. So this is one option that we have, the CDF, and this is the other option, the characteristic function. The probability distribution function or the characteristic function. Two different functions to describe psi. Okay? Now, let's look at this thing that we have here. So I write like this. Yes. So this is the expected value of e to the I psi x, right? Now, how can we write this in a different way? So I understand that you already had complex calculus, right?
We had it, I don't remember it.
Well, you have to know this, that's for sure. What is this? I psi and x.
Is that complex numbers?
ix plus I.
This is the cosine of psi x plus I sine of psi x.
Sure, plus 15.
You meant the degree.
Oh, I know. Yeah.
So, you know this. I hope you remember this. If you don't remember, just review what it is, right? So it means that we can write it as follows. So this is the expected value of the cosine of psi x plus I, the expected value of sine of psi x, right? So there are two different ways of writing this, okay? So it's hard to understand right now why do we need this e to the I psi and all of it, but you will see it, okay? So we have that. This is the characteristic function. Now, let's find, for example, the characteristic function of the Bernoulli distribution, right? For example, if Psi has Bernoulli distribution with parameter p, then the characteristic function of Psi, what is it? So what are the possible values for Psi if it has Bernoulli distribution? If you don't know this in the exam, you fail for sure. Believe me. What are the possible values for Psi if Psi has Bernoulli distribution? 0 and 1. Okay. So we need to. This is in general, right? So let's say that Psi has. So here, Psi is a discrete random variable. Then the characteristic function of Psi, what is going to be? It's going to be and Psi only takes non-negative integers, right? So what is going to be the characteristic function of Psi? It's going to be the expected value of Psi. So the expected value of e to the Psi x. Now, what is the expected value of e to the Psi x to the I Psi x if we know that Psi is discrete? We need to sum up all the possible values of Psi and multiply by the probability of Psi. So this is the sum from k0 up to infinity of e to the I k x, right, times the probability that Psi is k. This is clear? So this is just the expected value. So this is, right, the expected value of a function of Psi is just the function here times the probability that Psi is going to be k, right? We have I k x. Now, Psi here is discrete. Now, let's find the characteristic function of Psi if Psi has Bernoulli distribution. So the possible values are 2, 0 and 1. So what if we have 0? Then what do we obtain here? What is the probability that Psi is 0? Y minus p, right? Multiply by this in the point 0. So what do we obtain? 1, right? So times 1. Plus, what is the probability that Psi is 1? P. And what is this in the point 1? So e to the power of kx. Ix, sorry. That's it. This is the characteristic function of a random variable with Bernoulli distribution.
What is x? X is the random variable. What is x?
What is next?
Yes. This characteristic function, what is the domain?
Ah, you mean that? So this is a function from the real numbers to the complex numbers. It's of course to the complex, right? Because we have I here. And real, it can take any values, any real values. Now, what can we see? Okay, so this is the first one, okay. Now it's clear that to find it is very easy. All that we have to do is to find that. Now let's look at the properties. So the first property is that the characteristic function in the point 0 is what? What do you think? 1. Okay? So this is the first property. Now the second property is that the absolute value of the characteristic function is always less or equal than 1. Why this is true? Can you see it? why the absolute value of this function is always less or equal than 1. Let's prove it here, right? So we have the absolute value of psi of x. For psi of x, this is the absolute value of the expected value of e to the I psi x, right? And this is always less or equal than the expected value of the absolute value of this function. And what is this equal to? So as we already know, this is the absolute value of the cosine of of psi x plus I sine of psi x. So what is the absolute value of this function? Of the cosine of y plus I sine of y. You had complex calculus, right? No? So did you have it all or not? You are in the third year. You should have last semester.
International third year.
But still. No. So did you or no? Complex calculus. You don't remember? You have it. Okay. So what is this? What? So what is the meaning? Okay, what is a complex number?
With an I in it.
Well, okay. Do you remember at least this? I mean, so we have a complex number is a point on the plane, right? When we have here real numbers, here we have real numbers. So this is A, this is B, right? And our number Z is A plus IB. Right? So what is the absolute value of a complex number is this distance, is the radius, right, of this. In this case it's 1. Okay? No? Okay, if you don't remember this, please review that because it's important. So we obtain that this is 1. So the absolute value of the characteristic function is always less or equal than 1. And these things are important because I'm going to ask you, for example, is this a characteristic function or not? And you have to say yes, no, because maybe the value in 0 is not 1, or maybe because it can be greater than 1 or something like that.
The characteristic value is either 1 or less or equal to 1.
Yeah, so it's always less or equal than 1, the absolute value. Okay, this was the second property. So we have the first property, second property.
So also characteristic value can be negative infinity. It's also going to fall into the characteristic value. It's like not restricted.
Function, you mean?
It's a function.
No, because it's less or equal than 1.
So it's not restricted by 0. There's no restriction, only 1.
No, look. X can be any number. So it's something like this. So X, and this is the characteristic function, right? So X can be any real number.
Yes, sir.
But the function itself is going to be from -1 to 1, so somewhere here. So how it looks like. That's how it looks like. Okay. Okay. Now let's look at the third property. So what if we have that psi1 and psi2 are independent random variables, so such that psi1 and psi2 are independent. So let's find the characteristic function of the sum. So what is this? Let me do that over here. So let's find the characteristic function of the sum. this is by definition the expected value of e to the I, and here I have psi1 plus psi2 x, right? What I do next? What do I obtain here? No, just look at this. We have a sum here, so it means that we can divide this into two products, right? So the expected value of e to the I psi1 x times e to the I psi2 x. Now, what do we know about psi1 and psi2? We know that they are independent. How can we apply that they are independent over here? We know that psi1 and psi2 are independent, and we are looking at the product of two functions depending on independent random variables. So this is just the product, right? So we can apply like the expected value to this one and the expected value to this one. So this is the expected value of e to the I psi1 x times the expected value of e to the I psi2 x. So this is what? So this is the characteristic function of psi1, characteristic function of psi1 x times the characteristic function of psi2 x, right? Conclusion, if we have the two random variables are independent and we want to find the characteristic function of the sum, then all that we have to do is to multiply their characteristic functions. That's it. So from here we can conclude, right, so this is like some result, that if we have psi1, psi2, psi-n, and these are identically independent, identically distributed random variables, and we know that for every I, psi I has the same distribution that psi. So all of them have the same distribution. Right?
What does this acronym stand for? IL, we are used to independent.
Where?
So the I, this one, yeah.
Independent, identically distributed random variables. So all of them have the same distribution that psi. So this means equal over d means that they have the same distribution. Then the characteristic function of the sum is going to be just the product, right? So it's going to be just the characteristic function of psi to the nth power, right? So we have to multiply psi, the characteristic function of psi, n times, right? So we're going to apply this as well. So this was the property number 3. Now let's look at the property number 4. I don't know. Let's see. So what else? We have that. Okay. Yes, if the characteristic function of psi is always a real number, right? Because look, the characteristic function, I don't know, the characteristic function can take complex numbers, complex values, right? But if it is always real, then from this follows that psi and minus psi has the same distribution. What does it mean? It means that the probability that psi is between 4 and 5 is equal to the probability that psi is between -4 and -5. So it means, so from here follows that the density, the probability density function of psi is going to be an even function. It's going to be like this, for example. Again, if all the values of the characteristic function of psi are real, then it means that psi and minus psi have the same distribution. From this follows, you can understand that the value that psi, so the probability that psi takes values, I don't know, from minus 5 to minus 4 and from 4 to 5, so the probabilities are equal. It means that this area from here and this area are equal. And this is true for any value here and for any value here. Then, of course, the probability density function have to be an even function. So the same here should be here, right? Symmetry. We have symmetry. And this is the case, for example, if psi, so if psi has a standard normal distribution, the standard normal distribution. If psi has a standard normal distribution, we know that the probability density function looks like this, because we know that the probability density function of psi is something like 1 over the square root of 2 pi e to the minus x squared over 2, right? And this is this function. And somehow that's not true, but somehow we can understand that all the values of the characteristic function of psi, if psi has a normal distribution, are going to be always real, not complex. Okay? So this was the property number 4. Now, property number 5. Let's look at phi. So we have 5 psi of x, right? Right, so this is expected value of e to the I psi x, right? Now let's find the derivative of this in the point 0. So the derivative of this function the derivative of this is going to be what is the derivative of this? Is this, right, multiplied by I psi, right? We have I psi and the expected value of e to the I psi x. Now let's look at this in the point 0. What do we get? Here we get, in the point when x is 0, then we get that phi of psi prime here 0 is just equal to, here we have 0, so we have I psi. Wait. The value of xi. No, but xi is over here. Sorry. Xi is here. Xi is inside. So we have that the derivative is going to be e. We have I psi e to the I psi x. Yeah. Now let's look at this in the point x being 0, and we obtain that 5 psi the point 0 is just, what is it? Here we get 1, right? And then we obtain I and the expected value of psi. Okay? Now let's look at the second derivative. What do we have? So this is the first derivative, then the second derivative is going to be the expected value. We have again I from here, then we have minus, right? So this is going to be minus here. We have psi squared and e to the I psi x. And now let's look at the value of this in 0. What do we get? We get that the second derivative in the point 0 give us, this is going to be 1. So it gives us minus the expected value of psi squared. And we can continue like this. And we can see that this is minus, we can change it by I squared. Right? So from here we can conclude that the kth moment of psi, we can find it as the kth derivative of psi of the characteristic function of psi in the point 0 over I to the k. So now it's very easy to find the kth moment of a random variable. So what do we have to do if we wanted to find the kth moment of a random variable before? So if we know the density and we want to find this, what do we need to do? So we know the density of psi. Then if we want to find here, no, when we want to find the expected value of psi to the k. So look, if we know that psi has some density, then how do we find this? We have to do the following. The expected value of psi k is the integral from minus infinite to plus infinite of x to the k and times the density. So to find this value, the kth moment that we call, so the expected value of psi to the k, we have to find this integral. And this is sometimes is sometimes is not, right? Now all that we have to do is to find this function, and that's it. So for example, to find the kth moment, it is much better to use the characteristic function. Is the same. I mean, it's moment or momentum. Maybe it's. I call it second momentum. Maybe it's momentum. Am I mistaken? I'm not sure. We're talking about the same. So yeah, you can find. For example, if you want to find the variance, all that you have to do is instead of writing k, so you have to write 2, right? And here you have to write 2. So you have to find the second derivative of that, and that's it, right? So this is a huge property. It's very important, right? Okay, great. What else? So we have the characteristic function, tangent. We still have 15 minutes, so let's just finish, and we'll have a break for 15 minutes if you want. Yeah. So, what else do we need to define? Let me see what other property maybe can be useful. Yes, this one. So let's find, so this property number 6. Let's find the characteristic function of axi plus b. So this is easy, right? So xi plus b, just some random variable eta, right? Okay, so this is the expected value of e to the axi plus b, right? Times I times x times x. So we can write this in the following way. So this is the expected value of e to the I. Here we have a psi x and e to the I b x, right? So we are finding the expected value of psi. So here we don't have psi. So this is a constant, so we can put it here, right? And this is e to the I b x and expected value of e to the I a psi x. Now what is this? So we obtain that is equal to e to the ibx, right, this. And now let's write this. So this is the characteristic function in the point ax. Okay, so this is equal to the characteristic function of psi in the point ax. Well, and that's it. So this is equal to this. Okay, so we are going to use it also. This was property number 6. And what else? I think that's it for the properties. Yeah, and the last property is that, so this is a theoretical property like, so this function, so this property is number 7, so this function is always uniformly continuous. Uniformly continuous, I don't know.
How many properties are there?
This is the last one, 7. So do you know what is the meaning of this? What is the meaning of that?
It's not, can uniformly continuous, it's a continuous uniform.
Yeah, what is the meaning of that? So is every continuous function uniformly continuous? No, of course not. Is every uniformly continuous function continuous? Yes, it is. So what's the difference? Yeah, so it's this is like not clear, right? So look, for example, sine square of 2x. I don't remember exactly the function, but for example, you can take the following function. So here is like very close like this, and here it goes. So this function is continuous, but this function is not uniformly continuous. Uniformly continuous means that if you take any 2 points, x1 and x2, such that their difference is less than some beta, right? Then for every, for every beta, if for every beta we have this, then there exists some epsilon such that the function on this point is less than epsilon. So if we have that 2 points are very close, then the function, so the difference of the function defined here is also very close. Okay, so here you can take points which are very, very close. Their difference is 0.000001, but the values of the function is going to be very high. It's going to be, I don't know, 0.5. That is why this is not uniformly continuous. Okay, so that's somehow the meaning of uniformly continuity. And this is also from calculus from first year, right? So, so this function is like this. So this is useful if, for example, you are given with some function and you need to prove that this function is not a characteristic function. Then if this function is not uniformly continuous, then it means that it's not a characteristic function, right? Yeah, so, and the last thing for the characteristic function is that, do you know what is this? The Fourier transform. Did you have it already? Did you? Do you remember? No? You had it already, yes? Yeah. This is one full semester of calculus, I think. I don't remember, right? This is the third year, by the way, third year. Maybe next year, maybe next semester, I don't know. Anyway, this is something I'm not going to explain what is this, but the only thing that you need to know is that if you know that Psi has Psi has density, right? Then how do we compute the characteristic function of Psi? So the characteristic function of Psi, right? What is it? It's just the expected value of e to the I psi x by definition. So how do we compute the expected value of something if we know that we have a density? We have to compute the integral from minus infinite to plus infinite of e to the I xt, right? And times the probability density function, so by psi t dt. And this is called the Fourier transform of the density. So the characteristic function is the Fourier transform of the density function. This is just like some fact. You don't need to get it. You don't need to understand it. You just like need to know that there's such a thing, right? So the characteristic function is the Fourier transform of the density. And if you remember, there is something called the inverse Fourier transform. So if you know the Fourier transform of something, so you can find the inverse of it. So it means that if I know this, anyway, if I know this, I can find this function. So because this is the Fourier transform of this function. So if I know the Fourier transform, so this, I can find this function using the inverse transform. And it's equal to the following. So if we know that psi is absolutely continuous and that it has density, then we can find the density of psi as the integral from minus infinite to plus infinite of 1 over the square root of 2 pi, I think. E to the minus I xt and minus xt x and here's the x. Let me check that, I'm not sure. Minus I xt dt. Here is dt, sorry. And we don't need the square root. So that's it. So if we know the characteristic function, we can find the density. This is called the inverse formula. The inversion formula, maybe. Yeah. So that's it for the characteristic function. Next lecture we will state the central limit theorem, and we will prove it, and we will see what else we need to do. Okay. So that's it for the lecture. Let's take a break, and we'll continue with the seminar. So yeah, so you can find the density of psi1 plus psi2, right? The convolution formula. And using this convolution formula, we prove that if psi1 and psi2 are independent, and each of them, so psi1 has a normal distribution with parameters a1 and sigma 1 squared, and psi2 has a normal distribution with parameters a2 and sigma 2 squared, then psi1 plus psi2 has normal distribution with parameters a1 plus a2 and sigma 1 squared plus sigma 2 squared. So if two random variables are normal, then the sum of these random variables is also normal. But this is true only if they are independent. If they are not independent, this is not true. Why? Some example. So let's take that psi1 is just equal, so we take psi1 to have a normal distribution, right? And take psi2 being equal to minus psi1. So both of them have normal distribution, of course, right? Because it's minus, so it doesn't matter. So psi1 and psi2, so psi2 is just minus psi1. We have two random variables, okay? So what is the probability that psi1 plus psi2 is equal to 0? We know that psi2 is minus psi1. So what is the probability that psi1 plus psi2 is 0? So what is the probability that psi1 plus minus psi1 is equal to 0? So 1, right? So is this probability, so we can see that psi1 plus psi2, right, is just 0, constant value 0, and this is not a normal random variable with normal distribution, of course. Why? Because they are dependent. Okay, so this is like a very trivial example, but let me give you a good example of that. So what I want to prove is that if this is not true, I mean if they are dependent each other, then this is not true as well. Okay, so for this to be true, they need to be independent, right? So let's do the following. Psi has normal distribution, has a standard normal distribution, let's say standard normal distribution, right? And let's say that eta is equal to x psi, where x is a random variable, discrete random variable with two possible values, 1 and minus 1. It takes 1 with probability 1 over 2 and minus 1 with probability 1 over 2. And x, xi, and xi are independent. So in this way, we defined that eta, so we defined the new random variable eta. I want to, so, and you can see that psi and eta are independent, right? Because if, well, this we have to prove it, but let's say that this is all. So if we have psi, so eta is a function of psi. So eta depends on psi. If psi changes somehow, then eta also changes, right? So from here we can see that eta depends on psi, right? Now we can see that this is true, right? And we know that psi, it has normal distribution. Now, do eta have normal distribution? Yes, we have to prove it. How do we prove that eta have normal distribution? How do we prove that eta have normal distribution? We need to find the CDF of eta, and we need to get that the CDF of eta is equal to the CDF of psi. And if the CDF of two random variables is exactly the same, it means that they have the same distribution. So we want to prove, we want to show that psi has the same distribution that eta. So that eta also have normal distribution. To do that, we need to find the CTF of eta, right? So what is that? This is the probability that eta, and eta is x psi, probability that x psi is less or equal than y, right? And we can divide this probability into two cases because of the total probability formula. We can consider the case when x is 1, right? So because x can be 1 and x can be minus 1. So let's say that this is equal to the probability that x psi is less or equal than y and x is equal to 1 plus the probability that x psi is less or equal than y and x is equal to minus 1. Right? All that we did was dividing this probability into two probabilities. Now, x so here we can change that. So in this case we have that x is 1. So this is equal to probability of psi, right? We just are multiplying psi by x and x is 1. So psi less or equal than y and x is 1 plus the probability that psi less or equal than minus psi, right? We are multiplying by minus 1. So minus psi less or equal than y and x is minus 1. What do we know about psi and x? We know that they are independent. So since they are independent, and this is the intersection of two independent random variables is just the product, right? So this is the product, of two events in this case. The product of psi less or equal than y times probability that x is 1 plus probability that minus psi is less or equal than y, that y and x, times the probability that x is minus 1. So what is the probability that x is 1? It's 1 over 2, right? So this is 1 over 2, and this is 1 over 2, right? And we have this, okay? And now let me show you, look, what can we do with this? So we have the probability that minus psi is less or equal than y. Let's multiply by minus to both sides, and we obtain the probability that psi is greater or equal than minus y. Right? So this is the same. Now, what is psi? We know that psi has a standard normal distribution. So the density looks like this. Right? Now, let's take here to be y. So what is the probability? Here to be minus y and y. So what is the probability that psi is greater or equal than minus y? If this is the probability density function, is this area from here, right? Is the integral from minus y to infinity. Is the probability that psi is greater or equal than minus y. But we can see that this area is equal to this one, because this function is even. So we have symmetry. So this is equal to the probability that psi is less or equal than y. Right? So all of this is equal to half and half. So we have the probability that psi is less or equal than y, and this is going to be the probability that psi is less or equal than y. And half plus half, so we obtain y. So this is the probability that psi is less or equal than y. So this is the probability density function of psi in the point y. So what we prove, we show that the Ctf of eta is equal to the Ctf of psi. Since the Ctf of eta and the Ctf of psi are equal, it means that this is true. Both of them have the same distribution. So we conclude from here that eta has a normal distribution with parameters 0 and 1. Okay, good. Now we have that psi has a normal distribution with parameters 0 and 1, and eta has a normal distribution with parameters 0 and 1, and they are dependent. Now let's prove that the sum of psi plus eta is not normal. So here we have a new random variable psi plus eta, right? We need to prove that this is not normal. So that this is not true. Right? Then, what is the probability that psi plus eta is equal to 0? Let's find it. So this is the probability that psi plus, what is eta? Eta is x psi equal to 0, right? And this is the probability that psi, and here we have to multiply 1 plus x, right, is equal to 0. Now, what is the probability that psi is equal to 0? If we know that psi has a normal distribution, what is the probability that this random variable is equal to 0? 0, right? So this cannot be 0, so it means that this has to be 0. So x have to be minus 1. So this is equal to the probability that x is minus 1. What is the probability that x is minus 1? Is 1 over 2 here. So all of this is equal to 1 over 2. So we find that the probability that this random variable is equal to 0 is 1 over 2. What can we conclude from this? We can conclude that this is not an absolutely continuous random variable, because the probability that an absolutely continuous random variable is equal to something, to some given value fixed, in this case 0, is always 0. Okay? So if we obtain that the probability that this gamma is equal to 0 is 1 over 2, it means that gamma is not absolutely continuous. And if it's not absolutely continuous, of course it's not normal, right? So the sum of two dependent random variables is not, in this case, is not just the sum of, is not a normal. Okay, the sum of two normal dependent random variables is not normal. And this is the exercise number 8 from the homework, all right? So questions? Did you get it? What do you have to do here? So this kind of questions, I don't need you to solve this in the test, right? In the exam, but I can ask you. I can ask you that. We have that psi and eta are normal, but they are dependent. Are psi and eta, psi plus eta normal? You have to say yes or no. Yes, wrong, no, why, right? Just like that. I'm not going to ask you to give an example, but in general, you have to understand this. Okay, so theory is not only the lectures, but also seminars. I can ask you, for example, if we know that what we did today, we know, well, this is from the lecture, so yeah, I'm going to ask that. So we know that a sequence converges in probability. Does it mean that it converges almost surely? You have to say no. We have some example, right? And it's more or less like this. Okay, so this is important. Right. Now, let's continue with the next one. The next one is nice. So this is exercise number 9. Exercise number 9. We have the following. We have so randomly, so there's a segment, right, from 0 to 1. There's a segment from 0 to 1, and randomly we pick 2 points here. Point X and point Y. And of course, this distance is going to be some random variable psi, right? So we pick 2 points, and the distance between these 2 points is a random variable. The distribution of X, so X has a uniform distribution in 0 and 1, and Y also has a uniform distribution in 0 and 1, right? So we, with the same probability, we can pick this point in every part of the line from 0 to 1 for both points. We need to find, and we define psi as the distance between X minus Y, right? So the distance between X and Y, so X minus Y, the absolute value. We need to find the expected value of psi, and we need to find the variance of psi. And something similar to this is going to be in the test. Very similar. Not exactly the same, but very similar. So How do we find this? So let's find, so what are the possible values for Psi, by the way? Between 0 and 1, right? Maybe they coincide, maybe they are like very far from 0 to 1. Now, how do we find the expected value? So what is the expected value? Expected value of Psi is the expected value of this random variable, right? X minus y. So how do we find this? We need to use the density of the vector x and y. So this is going to be the double integral from minus infinity to plus, okay, from over all r squared, right? Of this times the density of the vector x and y with the points u and v, let's call it du, dv. That's it. This is what we need to find. How do we find this? Well, by the way, x and y are independent. So if we know that x and y are independent, then what is this? Sorry, not this included, but what is this if I know that x and y are independent?
The convolution formula?
No.
Just the product of their individual probability.
Thank you.
density.
This is the product, right, of the density of x and the density of y. Right, because they are independent. So if two random variables are independent, then the density of the vector is the product. Okay. Now, what is the probability density function of x? We know that x have uniform distribution. So what is the p? No. Continuous. So what is the PDF of Psi if Psi has uniform distribution between A and B? Rutika, do you know?
1 over b minus a.
Yes, 1 over b minus a, right? So what is in this case b and a? So 0 and 1. So this is 1 over 1, right? So this is just 1. Well, but not actually just 1, but 1 and the indicator function when u is between 0 and 1. So this is 1 for those values of u such that they are between 0 and 1. And this is also just 1 times the indicator function of v being between 0 and 1. So how does this changes? How does it change? So we need to change, here we have from minus infinity to plus infinity. So we need to change it from 0 to 1, right? And here from 0 to 1 again. And then I have x minus y. I have to write, sorry, I don't have to write x minus y here, but u. u minus v. And I have to write this, so 1 times 1 du dv. That's it. This is what I have to find. How do I find this integral? So let's say that this is u, this is v, right? So let's put this u over here. So this is going to be the integral from 0 to 1 of du times the integral from 0 to 1 of u minus v dv. What does it mean that we have u minus v? U minus v is equal to u minus v if this is greater than 0, and u minus v is v minus u if u minus v is less than 0, right? So let me write that over here. So u minus v, just u minus v, if u minus v is greater than 0, and this is v minus u, and if u minus v is less than 0, right? So we can consider both cases. So this is going to be the integral from 0 to 1, and we have du. And now, if I have, okay, let me draw that over here. This is u, this is v, this is 1, this is 1. This is u equals v, right? So in the first case, I will have that u minus v is greater than 0. So u is greater than v, right? So here, u is greater than v. So I have to take the integral for v, right? For v, taking values from
Creo que no te entiendo.
from 0 to u. Okay, from v, taking values from 0 to u, yes, of u minus v, right? And the integral from, in this case, we have v minus u, and u is less than v. So v is greater than u, so this. So we take the integral from u to from u to 1 of v minus u. So here we have dv, and here we have dv. Yeah, so what is this? Okay, let's find the integral of this. What is the integral of that? We have to, we have minus here, so we will have u dv. What is the integral of u dv? Is u times v from 0 to u, right? Minus, we have v dv, so v squared over 2 from 0 to u, plus v dv, we have v squared over 2 from u to 1, minus u dv, so u v from u to 1. Okay, like this, and that's it, right? Now, what do we obtain? Well, you can do this, right? All of this to replace it, And at the end, you should get, if I'm not mistaken, 1/3. So we don't have much time. 1/3. Let me check if that's correct. Yeah, that is correct. So the expected value of the distance between x and y is 1/3. You can do it later. It just would take us 10 minutes for sure. So is this clear? You have something like this, but with circles, not with the line. So the variance, how do we find the variance? Let's find the variance. So we already know that the expected value of psi is 1/3. So if we want to find the variance of psi, what do we need to do? The expected value of psi squared minus the expected value of psi, all of this is squared, right? So we need to find this. So we need to find the expected value of psi squared. What is this? This is just the integral. From 0 to 1, here from 0 to 1. And here we have x minus y squared. Sorry, u and v. Where do I have? U minus v squared and du dv. How do you solve this? Well, you just have to, this is squared, u squared minus 2uv minus, plus v squared, and you can solve it yourself. I mean, this is already, you can never solve, and you will get, I don't know, what will you get? You will get 1/18. No, wait. 1/6. And from here, we can conclude then that the variance is 1/6 minus 1/3 squared. So 1/6 minus 1/9. Well, you can compute the final answer as well. So we can find the expected value of this distance, and we can find the variance. Right. So again, and this is very important, if you have some random variable which depends of other random variables, psi, eta, for example, right? And you want to find the expected value of this, you have to compute the double integral, and you have to write the function here, and you have to write the density of this vector, psi, eta. This is very important, all right? And this is what we did, actually. That's it. And that's it with this homework. Now let's continue with the next homework. The next homework is already on characteristic functions. So by now we're finished with, no, we're not finished with integrals by far. Anyway, so first, the sign of t. Is this a characteristic function or not? (0.5 extra). You have to tell me yes or no and give me the reason. Is this a characteristic function or not? So
it is characteristic because it's between 0 and 1.
Not enough? Not enough? Okay, 10 seconds more.
If we got the graph of sine 1. Therefore,
That is true, yes, but it's not enough.
What?
5 seconds. You have 0.5 points that you can get. I don't know why you don't want it. I understand, really.
maybe if we manipulate it, if we differentiate it.
Okay.
No, it's not.
Why?
By the definition.
What definition?
So it's e raised to power I and some random variable times x.
So what?
So if it's only possible if I equals to I squared. That's why.
No, that's not a reason. Okay, that's it. You lost your chance. What is the first property of a characteristic function? Please tell me. You don't take notes, huh? I don't know how you're going to.
So phi of 0 should be equal to 1.
So
The
the
first
first
property.
yes. So the first property is that the characteristic function in the point 0 is equal to what? 1. To 1. No, you didn't mean that. So what is the sign of 0? 0. So it's not a characteristic function, right?
Oh my god,
I told you. I mean, it's very easy. I don't say much. Anyway, so that's all that you have to do. You have to look at the first property, say, okay, let's change sign of 0. It's 0. No, it's not, right? It's very easy. So don't say that you didn't have chance. So no, the answer is no, it's not. Because of this, the sign of 0 is 0, and the characteristic function in the point 0 always should be 1, right? Now, number 2, the cosine of t. Is this a characteristic function or not? 0.5, you can tell me which random variable. I'm sure you are not going to get it.
this is the characteristic function.
Yes, it's a characteristic function. Why?
Because cos of 0 equals to 1.
Yeah, but it is not enough, right? There are many functions which in 0 is 0, and this is not a characteristic function.
It is between 1 and 0.
Yeah, it's not enough. The only way to prove it is to tell me which. So let's say that this is the characteristic function of some psi t, right? What is psi? What is the distribution of psi? If you can tell me this, I give you 1 point. 1 point in the final exam.
It says minus infinity to positive infinity.
Right? What?
From negative infinity to positive infinity?
No. What is the distribution of psi? If you can tell me this, I'm ready to give you 2 points in the final exam. 2 points.
Sir, I took a picture of the distribution.
You have 10 seconds.
Yes. Type of convergence.
10. What do you mean uniform?
Uniform distribution.
Where? In which values?
Between 0 and 1.
No.
Yeah. It's the same as the one we did at
Between negative infinity and positive infinity?
Nope. You are not going to get it. All right. So look. Yes, the answer is yes. Psi can take values 1 and minus 1 with probability 1 over 2 and 1 over 2. Why, you say, right? What is this? E to the I psi x. You know that this is just, this is the cosine of of psi x, right? Plus I sine psi x, right? Now, what if we take e to the I psi x plus e to the minus I psi x over 2? What is this? This is the cosine, right? Of the cosine of x. Wait. Dun, dun. Ah, yeah, this is cosine of t, but x. What about psi x? Anyway, this is the cosine of. What about psi? Ah, okay. So look, what is this? This is the cosine of psi x plus I sine x, right? And here we have cosine of psi x minus sine of psi x, so minus go with minus, and we have half and half, so we have 1. So this is actually psi here, right? So what is it? Wait. So we have still minus. What about with this psi? Why do we have the psi here? What am I saying? Like this, like without psi over here. I'm sorry. Yeah. Just x, right? X and x. So this is the cosine of x, right? So we have this. This is the cosine of x. So what is this? This is the expected value of e to the I psi x. What are the possible values of psi? 1 and minus 1. Let's take 1. So this is going to be e to the I x times the probability that we get 1 over 2, plus minus 1, so e to the minus I x times 1 over 2. And this gives us the cosine, right? So yes, this is a characteristic function, right? Now, okay, four. How many points? I don't know. This looks like I don't know. Anyway, for half, only half. Is this a random variable or not? Sorry, a characteristic function or not?
Yeah. Yes.
Why?
Because if you put 0, it's going to be 1.
No. I hope you are not looking in your phone. The answer is yes. Why? I told you, if we have psi1 and psi2, and they are independent, right? And we want to find the characteristic function of their sum, then we need to look at the product. So psi1 have which distribution? Well, this one, right? Because we have, so this is just cosine of t times the cosine of t, right? So this is a characteristic function of this random variable, which psi1 and psi2 have this distribution, and they are independent.
But if t equals to 0, what does cos squared of 0 is? 1.
Yeah.
So let's say to yes, because if cos 0 equals to 1, so it doesn't.
No, there isn't enough. Psi1 and psi2, not the same. Okay, look. These are different things, all right? This means that they have the same distribution. This means that they are the same. Okay? Different.
We missed 1.5 points.
Yeah, you. Okay, the cosine of t squared. Is it or not?
0.5 points.
0.5. Why? This is not easy, so I can tell you. The answer is no, it's not. And that's because this function is not uniformly continuous. So this function looks like I told you before. So this is the reason why this is not characteristic function, right? Now, and finally we have some other, this number 5, right? 1 over 1 plus t squared, I think. The answer is yes, and this is the characteristic function of the Laplace distribution. But to prove it is really hard. I mean, it takes like 30 minutes to find it, so we're not going to do it. The answer is yes, for the Laplace distribution. Laplace distribution with some parameters. I don't remember the parameters, all right? Okay, good. Now, this was exercise number 1. Now, exercise number 2. For 0.5 points, who can find if Psi, without looking at the phone, if Psi has a binomial distribution with parameters np, what is the characteristic function of Psi?
So here we have expected value as NP.
Again, please.
So here we have expected value as NP.
Yes.
Okay, and so if we put it in the formula, so it will be like NP multiplied by, no, E multiplied by E, E to the power iota of psi x. And then we put expected value.
Yeah, but so what is the probability that Psi is k in this case? If Psi,
NCK,
huh?
NCK,
N choose k, p to the k, 1 minus
Q to
p,
the,
n minus k. So if you want to find this, you need to find the sum from 0 to infinity, sorry, to n of k, sorry, of e to the I k x multiplied by all of this. So it's not very easy that way. I mean, how are you going to find this thing? Well, you can find it, but
2.5 points.
I don't think people can answer this in 10 seconds. This is coming to the board. So.
Yes, sir, we're suing for defamations. Everybody gets 0.5.
look. Let me prove you that. Let me prove you that you're wrong. Okay, look. Well, where is it? Where is it? Where is it? Where is it? I don't see it. Ah, here. Again, the same thing. If I know that I have some random variables, and the sum, and they are independent, then the sum is going to be just the product, right? Yeah. What do I know of a binomial random variable? If Psi has binomial distribution with parameters np, then Psi is equal to Psi1 plus Psi2 plus Psi n, where Psi I has Bernoulli distribution with parameter p. We already found this. So it means that the characteristic function of Psi is exactly the same to the characteristic function, so they are like this. So they have the same distribution. So this is exactly the same to Psi1 up to plus Psi n. We know that Psi1 up to Psi n are independent, so this is just the product. And they have the same distribution, so this is the distribution of Psi I to the n. And we found this in the lecture. This is 1 minus p plus p e to the I x, everything to the n. So all that we have to know is this property, no more. Right? The whole lecture today was looking at the properties, so it means that this is all that we need to use, no more. Right? We don't need to compute anything, just look at the properties. So this is the characteristic function of Psi if Psi has a binomial distribution. Now, let's look at Psi if Psi have a standard normal distribution. Let's find the characteristic function of Psi. How do we find the characteristic function of Psi? Well, again, this is the expected value of e to the I Psi x, right? So this is the integral from minus infinite to plus infinite of e to the I Psi x and tx, I tx, and I have to multiply it by the density of Psi in the point t, dt. This is all that I have to do. What is this? So this is the integral from minus infinite to plus infinite of e to the I tx, right? And 1 over the square root of 2 pi e to the minus t squared over 2 dt. So what do I have? Look, I have I tx and I have minus t squared over 2. I want e to the minus x squared over 2 to be alone, right? So for doing that, I will get e to the minus t, here minus ix squared over 2. This is exactly the same, so I'm just putting together this and this, and I obtain this. You can check that. D T. For 0.5 points, what is this? Krutika, do you see?
So it's E minus open bracket T minus IX.
Mm-hmm.
Okay,
So what e raised power minus what do you write on the right?
Here? Yeah. This is t minus ix squared, all of these squared.
2 over 2 pi.
No. So look. What is this? All of this?
this is the characteristic function.
No. This is the density of a random variable with what distribution? A in this case is this thing, Ix, right? And sigma squared is 0. Sorry, not 0, but 1. No, this is the density. So the density of this random variable. And we are taking the density of a random variable from minus infinity to plus infinity. So this is 1. So this is what we're left with. So all of this is just e to the minus x squared over 2. Now we found the characteristic function of a random variable with normal distribution, right? Now let's find a characteristic function of psi of eta. Okay, eta, we already have psi of eta if eta has a normal distribution with parameters a and sigma squared. How do we do that? So we already know, and we already proved that eta has the same distribution that the square root of sigma squared times psi plus a. We already proved this 2 times, I think. So this and this have the same distribution, okay? Where psi has, so psi again has a normal distribution with parameters 0 and 1, and eta has a normal distribution with parameters a sigma squared. We use this to find the expected value of the of eta. Now, how can we find this? So the characteristic function of eta is equal to the characteristic function of this. Now we have this, and we can look at the property that we had before. This one, this property. So look, this is the answer. We have axi plus b. So this is going to be, apply this property, going to be equal to EIB, in this case b is a x, times the characteristic function of psi in the point ax. So a is this, right? And what is this? We just found it. So the characteristic function of psi in the point x is e to the minus x squared over 2. Here we don't have x, we have the square root of sigma squared x. So we just have to put, instead of writing x, we put all of this. So it's e to the I ax times what? That, e to the minus x squared, so sigma squared x over 2. This is the characteristic function of eta. So of a random variable with a standard normal distribution. Right? Yeah.
Can we finish for today?
Yeah, sure. So for your homework, you have to solve. You have to try to find at least some characteristic functions, and yeah. So see you next week.
Sir,
Yes.
sir, can you hear me?
Yes, I can.
Yes, in this case where you wrote instead of x square, you substituted it by under root of sigma square. Why isn't x square in the final answer?
Because we have the square root here, the square root of sigma squared. So a square
Yes,
root.
yes, but why not for x square? I mean, when we had phi of x, we got the answer as e to the power minus x square by 2, right?
Mm-hmm.
When we had the function x, we had my e to the power minus x square by 2. So it will be whole square, right? So under root of beta, whatever that is, sigma square x, the whole square, or no?
The whole, yes. The whole of this. I don't know if that's what you're asking. Though this whole is going to be a square.
Yeah, so why not x square in the final answer?
Thank you.
Oh, okay. No, I just thought I was getting it wrong. Okay.
Yeah. That's it.
Okay, thank you.
Bye.